All right, guys, Mr. Antonucci here, and we're starting section 6.2, which is growth and decay. And we're going to talk about using separation of variables to solve a simple differential equation in this quick video here. So up to this point, we've learned how to solve two specific types of differential equations. One where, whoa, that's way too big, where y um, is equal to y prime is equal to f of x, and y double prime is equal to f of x. So basically, those two we've learned how to solve algebraically. And we've also looked at numerical and graphical methods with Euler's method and slope fields. So now it's time to tackle a more general type. The key idea is to rearrange the equation so that each variable appears only on one side. This technique is called separation of variables. And we're actually going to dive deeper into this in the next section. We're going to do a whole section on separation of variables, but we're just going to look at the basics here with this particular example. So if we want to solve the differential equation y prime equals 2x over y, first thing we can rewrite it using dy dx equals 2x over y. And then what we do is we separate the y's and dy's on one side and the x and dx's on the other. You can't do this with every differential equation, only under certain circumstances, but like this one, it's very easy to separate because you just multiply the y to the other side and the dx to the other side like this. And then you just slap an integral symbol on it, anti-differentiate both sides. So this one would be y squared over 2 equals x squared plus c. Now notice I put the plus c only on the right side. Essentially what happens here is on the left side you would have plus c, and on the right side you would have plus c. And they could be two different constants, we don't know. But if you subtract c1 from both sides, when you combine these like terms, they're just going to be a constant anyway. So you don't really have to worry about that. So we just put plus c on one side and leave it like that. Okie doke. All right. So if we could solve this for y squared equals 2x squared plus c. Again, I don't need to multiply the c by 2. I could if I wanted to, but still it's going to get absorbed into the constant anyway when I solve for the particular solution. So this would be the general solution. Now, sometimes you might be asked to express it as a function, or in other words, solve it for y. If we had to do that, you would take the square root of the other side, like this, but you would need a plus or minus over here because when you take the square root when solving an equation, you need to account for the plus or minus. Then, given whatever the initial conditions are, you would determine if you wanted the positive or the negative part of that. Okay, but we're going to use the y squared version to find the particular solution that passes through the point 1, 1. So all we do is plug in the point 1, 1 and solve for c. So 1 equals 2 plus c. So c equals -1. Now, we don't want to stop there. That's not the final answer. We want the value c plugged in to get the particular solution. So y squared equals 2x squared minus 1. And that would be our particular solution. Now, had we been asked to solve the equation for y like we were over here, we would have to make sure that when we plug in 1 comma 1 and the value of c, which is -1, that the equation works. So in other words, we would have to have the positive square root here like this, because when you plug in 1, you want to get the y value of +1. Okay. Had the initial condition been 1 -1, then that would have resulted in the negative radical. Okay. All right, guys. Well, that's it for this first part of this section. Hope that was helpful to you. Reach out if you have any questions.